Did you know that one mistake could cost millions of lives? In this story, the USA decided the fate of the war in just a few days. If you're interested in the truth about World War II, subscribe and hit the like button. There are many shocking facts ahead. June 7th, 1940. Chrysler headquarters in Highland Park, Michigan. Picture the desk phone ringing one of those heavy black instruments and a conversation that would run exactly 7 minutes. 7 minutes that, improbably, would tilt the axis of modern warfare. On the line, William Knudsen, just named by President Franklin Roosevelt as Commissioner of Industrial Production. His question sounded almost reckless. Could Chrysler build tanks? At the other end sat Kaufman Thuma Keller, the chief executive of Chrysler Corporation, a man not given to bluff or bravado. His reply landed with plain-spoken force. "I don't know. I've never seen one of these things." Now, hold that image. At that instant, the United States Army possessed precisely 66 medium tanks, no more. Nazi Germany, in a little over a year, had hurled more than 3,000 panzers across the map of Europe, smashing Poland in 26 days and driving through France in 6 weeks with the ruthless choreography of coordinated armored warfare. Ask yourself, how long would America's entire tank force have lasted in the teeth of Blitzkrieg? Before lunch on any given day, the arithmetic of disaster was etching itself, line by crimson line, onto Europe's battlefields. Neither Knudsen nor Keller could have known that their brief exchange would light the fuse of the most sweeping industrial metamorphosis in military history. Imagine the audacity. Within 9 months, Chrysler would do what government arsenals had never dared to dream turn tanks. Those 30-ton behemoths that once demanded months of patient handcraft into items of flow production. They would emerge like automobiles, one after another, one every 55 minutes at peak. What happens when you weaponize the assembly line itself? You shatter every old assumption about how armies are equipped, and you prove that American industrial ingenuity can turn production into a strategic instrument. But first, the obstacle staring everyone in the face. In June 1940, the United States ranked 19th in military power, behind Portugal. The Army counted more horses than tanks. The Ordnance Department, guardian of weapons development, still moved to the rhythms of the First World War. Tanks were built by hand in government arsenals, each vehicle a bespoke artifact requiring master craftsmen. Consider the Rock Island Arsenal in Illinois. At full stretch, it might complete 3 medium tanks in a month. From raw steel to field-ready machine, a single tank consumed 12 weeks. Germany's Panzer Works, though also grounded in craft methods, enjoyed the momentum of years of covert rearmament. By 1940, German manufacturers were delivering 1,400 tanks annually from multiple factories. Britain, quicker to mechanize than the United States yet still constrained, managed about 1,000 a year. Across the great powers, the consensus was ironclad. A tank was a sophisticated weapon system, the province of specialists, custom shops, and months of careful fitting and adjustment. Could anyone break that spell? Keller ended the call and moved instantly. He summoned his chief engineer, B.E. Hutchinson, and Frank Zader, Chrysler's vice president of engineering. Within the hour, the 3 men were in Keller's office, door shut, the air thick with the sense of a wager that bordered on impossible. The Army's ask was stark. They wanted 1,000 medium tanks. They wanted them in less than 18 months. And they wanted Chrysler not merely to assemble machines, but to conjure an entire system from nothing design the factory, invent the methods, and deliver finished vehicles with a team that had, moments earlier, admitted it had never laid eyes on a tank. Hutchinson broke the silence with the only question that mattered at the outset. What's the current production time for a tank? Zader had come prepared. Rock Island Arsenal, he said, builds 3 M2A, 1 medium tanks per month, 12 weeks per unit, skilled craftsmen end-to-end, components hand-fitted. As you hear that cadence 3 per month, 12 weeks each, ask yourself, how do you bend time like that? How do you compress an art into a process and a process into a rhythm without breaking the machine or the men who must build it? The room understood the stakes. Outside, the world was burning. Inside, 3 engineers of American industry were about to attempt the unthinkable, to take a weapon that had been the child of artisans and teach it to be born on a line. Imagine you were there, pen poised over a blank sheet, told to redraw the very blueprint of war. Where would you begin? Hutchinson ran the numbers on the spot. At the prevailing pace, he calculated, producing 1,000 tanks would take 277 years, 2 centuries and 3/4, when the Army needed them in 18 months. Feel that gap like a chasm underfoot. What answer could bridge it? Keller's would set the tone for everything that followed. We won't build tanks the Army's way, he told his team, his voice a hammer on the anvil. We'll build them our way. If they expect 1,000 in a year and a half, they'll have to accept automobile production methods, and for that, we must see exactly what we're making. Within days, the trio was at Rock Island Arsenal. Picture yourself peering over their shoulders as they move along the shop floor, armor plates coaxed into place by hand, track tension judged by eye, memory, and the fingertips of experience, components custom machined on the fly to tame wandering tolerances. The model under construction was the M2A1 medium tank, a 19-ton machine carrying a 37mm gun. Each vehicle demanded roughly 8,000 separate parts, each part made to such loose tolerances that only a skilled craftsman could persuade them to fit. No 2 tanks emerged as true twins. Keller grasped the core flaw instantly. This isn't manufacturing, he said, watching the dance of files and shims. It's sculpture. Everything rests on the artisan's hands. You can't scale it. You can't train enough new people fast enough. And you certainly can't turn out 1,000 in 18 months. Would you have argued with him standing there amid the clang of hammers and the hiss of welds? Back in Detroit, they convened what would become their clandestine war room, the Tank Committee. Think of a commandeered conference room at Highland Park, its walls filling with diagrams and process charts, the ashtrays overflowing by dawn. Alongside Keller, Hutchinson, and Frank Zader were Owen Skelton, Chrysler's chief production engineer, and specialists in tooling, metallurgy, and logistics. They met daily, often through the night, grinding at a single riddle, not merely how to work faster, but how to work differently. The breakthrough arrived when they inverted the problem. Instead of asking, how do we speed up tanks? They asked, how do we change what it means to build a tank? Skelton voiced the pivot with the calm of someone aligning numbers on a ledger. An automobile, he said, is 2,000 pounds of steel, rubber, and glass built from 5,000 parts. We make 3,000 of them a day at Highland Park. A tank is 30,000 pounds of steel assembled from 8,000 parts. The only difference is what we're assembling. Let that sink in. If a tank could be treated as a mechanical assembly rather than a priestly artifact, then the gospel of automobile production might apply. But this demanded a ground-up reimagining first principles, not patches. Every component had to be redesigned for mass manufacture. Every assembly sequence had to be re-engineered for line work. Quality would have to migrate from the craftsman's intuition to measurable, enforceable specifications. When the committee dissected the M2A1, the picture sharpened. Fully 60% of the build time was being swallowed by custom fitting and adjustment. Parts made to arsenal tolerances wandered so widely that assemblers were perpetually adapting, shimming, and trimming. Hutchinson set a match to the old logic. We manufacture every component to automobile tolerances, he proposed. Then the parts will fit without adjustment. To military engineers, this bordered on heresy. Tank components endured stresses far beyond those in cars. Achieving automotive precision would mean new tools, new suppliers, new inspection regimes. Yet the payoff was undeniable. An assembly that took roughly 500 man-hours with hand-fitting might fall to something like 150 man-hours if precision parts simply bolted together. Ask yourself, what would such a collapse in time mean when the clock was measured in lives? Skelton pushed the thought to its rightful conclusion. If this was truly automobile production, the factory floor must change shape. No more stationary hulls encircled by artisans like surgeons around an operating table. Instead, a moving assembly line that carried the work to workers fixed in place, each trained for a specific, repeatable operation. Visualize it, the hull riding past jigs and fixtures, operations clicking into sequence, time becoming a metronome rather than a mystery. By November 1940, the committee had codified what they named the Chrysler method for tank production. Here was the blueprint. Every major component produced to precision tolerances on automotive machine tools. Armor plates standardized and truly interchangeable. Hulls welded in production jigs instead of being coaxed together by hand. Turrets seated on standardized rings. Drivetrains incorporating as many existing automotive parts as possible. And final assembly executed on a moving line with specialized stations. Could such a system really tame a 30,000-pound war machine? Keller carried this plan to the Army Ordnance Department that November. The reception was chilly skeptical, even hostile. To the career engineers of the arsenals, tanks were not merely machines. They were crafted instruments that survived because of the very handwork Chrysler meant to abolish. What would you have thought, sitting in that room? Would you cling to the methods that had carried you this far, or wager everything on a line that promised to turn the art of building tanks into the science of assembling them? The objections came fast and sharp. Automotive tolerances, the Army engineers argued, were too delicate for the punishing life of a combat vehicle. Moving assembly lines? They would spell chaos. How could you guarantee quality when the work never stopped moving? Welded armor, they insisted, was weaker than the time-tested, riveted plates. And as for Chrysler's promised rate of 10 tanks per day, pure fantasy. Keller met their skepticism with a single, unanswerable question. You need 1,000 tanks in 18 months, he said. We can deliver them. Can anyone else? Silence hung heavy in the room. No one could say yes. And so, in late November 1940, Chrysler won a contract unlike any in American history. The Army would pay to construct a dedicated tank factory from the ground up. Chrysler would design it, equip it, and run it. There was one stipulation. The Army demanded that the facility's design come from Albert Kahn, the architectural genius who had reshaped Detroit's industrial skyline. Kahn, now 71, was a German-Jewish immigrant who had arrived in the city as an 11-year-old boy in 1881. He had never seen the inside of an architecture school. His education was the hands-on grind of apprenticeship. By 1940, his firm, Albert Kahn Associates, employed 600 architects and engineers and had drawn up nearly one-fifth of all architect-designed industrial factories in the United States. Kahn's gift was not merely design, it was vision. He treated factories as vast machines in their own right. His buildings breathed efficiency. Glass walls flooded interiors with light. Floor plans directed the flow of materials like arteries, and reinforced concrete replaced the old steel skeletons, creating open, flexible spaces that could be built faster and adapted endlessly. His earlier triumphs, the Ford Highland Park plant and the River Rouge complex, had made automobile mass production possible. Now, war demanded that genius again. When Keller approached Kahn in early July 1940, the list of requirements sounded impossible even by Detroit standards. The new arsenal had to be colossal enough to contain a full tank assembly line and its component workshops. It had to rise in mere months, ready by April. It had to withstand bomb strikes. And when the war was done, it had to be convertible to civilian industry. Kahn listened, nodded once, and accepted. Then he unleashed his entire firm. For weeks, teams labored 18-hour days, sketching, drafting, and redrafting. The result would be christened the Detroit Arsenal Tank Plant. Under one roof, it would cover 1.25 million square feet, one of the largest industrial buildings on Earth. Its vital sections were walled in 3-foot-thick concrete, designed to shrug off direct hits. Steel trusses laced the roof, angling to deflect blast waves away from windows and vents. The building's layout itself was a physical embodiment of the Chrysler method. A main assembly line stretched nearly a quarter mile from end to end, a river of steel in motion. Feeder lines branched off like tributaries, feeding in engines, hull sections, and turrets at meticulously timed intervals. To the north lay the machine shops, where drive systems and precision components would be born. To the south, the welding bays where armor hulls and turrets took form in showers of sparks. The entire design was a single flowing sequence, raw steel entering at the west, finished tanks rolling out at the east, ready for war. And then came Kahn's masterstroke, an idea no military engineer had conceived. The assembly line would not run on the floor, but beneath it. He designed a 4-foot-deep sunken trench for the line, so tanks could glide through the building on carriers while workers stood at floor level, reaching every part of the vehicle without jacks or pits. The time saved, hundreds of hours per unit, was staggering. Suspension systems, drive trains, all could be installed swiftly and safely. On September 9, 1940, the first shovels hit dirt. The chosen site, 113 acres of former farmland in Warren Township, just north of Detroit, offered rail connections and proximity to Chrysler's nerve center. Construction erupted at a pace that defied logic. Crews poured concrete, raised walls, and laid utilities all at once in a controlled frenzy. Kahn's use of reinforced concrete meant each section hardened fast, strong enough to bear weight within days. If you'd stood there watching the skeleton of the arsenal rise against the Michigan sky, you might have felt what Keller, Kahn, and their men must have felt, that they were not just building a factory, but forging an engine of victory, one that would soon begin to breathe, to thunder, and to change the course of a global war By February 1941, the great shed of the arsenal stood up, but not yet alive. The main structure was there, walls shouldering the winter wind, a roof keeping the snow at bay, but the building still felt skeletal. Window openings gaped. Interior systems were a maze of unfinished runs, and yet the rail spurs kept delivering machine tools that were hauled inside and erected while masons and electricians worked around them. Can you picture that choreography cranes setting lathes as plaster dust drifted through raw corridors? Here was the breathtaking audacity of the schedule. Chrysler had promised the first tank by April 1941, even though the factory itself wouldn't be fully complete until May at the earliest. Keller issued the order that would pass into legend. We'll build the first tanks inside an unfinished building. And so they did, under conditions that would make most managers blanch. February and March in Michigan are merciless temperatures knifing below freezing. The Detroit arsenal had its skin of walls and roof, but the heating plant was not yet online, and glazing crews were still setting panes. Workers bolted and riveted in heavy coats, hands numbed, breath fogging the air like smoke. The workaround? They brought a steam locomotive inside the building, its boiler panting warmth into the immediate work zone. Imagine it, an engine meant to pull trains now stationed indoors, coughing steam to warm the men who were assembling tanks. This wasn't elegant planning. This was industrial will, bending the world to its timeline. Meanwhile, the tank committee kept knocking down engineering roadblocks. The drivetrain was the first big snarl. The M2A1's transmission had been conceived for hand assembly, fussy, slow, and unforgiving. Chrysler's engineers reimagined it with automotive logic, turning it into a unit that could be built on a dedicated line and lowered into the hull as a complete module. Assembly time plunged from 40 hours to 4. Ask yourself, what does it feel like to win back 36 hours on a single operation? Suspension demanded the same ruthless simplification. The team standardized every component, then designed fixtures so subassemblies could be built and tested before ever touching the hull. A complete suspension bogie could be put together in 2 hours and then bolted on in 20 minutes. No more hovering mechanics guessing it fit. This was choreography set to a stopwatch. The armor hull, though, was the monster in the room. Traditionally, tank hulls had been stitched together with rivets, each hole drilled by hand, each rivet set by a skilled team, a process that 8 weeks. Worse, under impact, those rivets could shear inside the crew compartment with lethal fragments. Chrysler proposed a radical fix: all welded hulls. The Army balked. Welded armor had no combat record. Heat from welding might embrittle plates. And welding, they insisted, was a black art requiring master hands. Chrysler answered point by point. Ballistic tests showed their welds outperformed riveted joints. Heat treatment protocols eliminated stress concerns. Production jigs located every plate with mathematical certainty. And here was the shocker: semi-skilled workers could be trained in 2 weeks to lay acceptable welds. Would you have bet against that with the clock ticking? By March 1941, component production was humming. The tank slated to roll out in April would be a child of the Chrysler Constellation, parts machined at multiple facilities, converging on Warren for final assembly. The engine, however, posed a thornier problem. The M2A1 was designed around Continental's R975 radial aircraft engine, a dependable 400 horsepower plant. But Continental couldn't deliver the volume required. Chrysler needed an immediate alternative. Enter engineer Harry Wilson with an idea that sounded like mischief. Chrysler had been developing a new inline six that produced 115 horsepower. What if, Wilson asked, we combined 5 of them into a single power unit? Absurd on its face, 5 separate engines yoked to a single output demanded a spiderweb of gears, shafts, and synchronization. But Chrysler's engineers relished the naughty and the new. Under Wilson's direction, they gave form to the A57 multi-bank engine. Picture it, 5 complete inline sixes arrayed in a ring around a central gear case, each crank feeding a gear that meshed with a common output gear. 30 cylinders in all, displacing 253 cubic inches, delivering 425 gross horsepower, 370 net through a single shaft. Outlandish? Absolutely. Unprecedented? Without question. Effective? Brilliantly so. The multi-bank solved problems in a single sweep. It exploited existing tooling and familiar parts so production could start immediately. It required no exotic alloys or rare processes. And because the work was modular and jigged, relatively unskilled labor could assemble it by following clear procedures. The Army disliked it on principle, dismissing it as a Rube Goldberg contraption, but they could not dispute the calendar. April 12, 1941, the day before Easter Sunday. Hold that date. You can almost hear the factory catching its breath, the locomotive's boiler sighing, the conveyors ticking as the promise made in winter moved toward becoming a machine of war. The Detroit Arsenal still looked like a work in progress. Sections of the great shell had no walls at all. Window openings yawned empty from one end to the other. The heating system remained a tangle of unfinished pipe. And yet, down on the assembly floor concrete, something wholly finished stood waiting. The first Chrysler-built M3 medium tank. Think of the M3 as a direct descendant of the M2A1, but muscled up for urgency, its main 75mm gun housed in a hull sponson, with a 37mm gun in a fully rotating turret above. Even as it debuted, the configuration was already showing its age, a compromise between what was proven and what was immediately necessary. But here is the revolution. This was the first tank ever born from an automobile-style assembly line. That single fact mattered more than any silhouette. 12 days later came the formal moment. On April 24, 1941, the completed M3 rumbled out of the still unfinished factory into bright spring light, past ranks of military brass, Chrysler executives, local officials, and the very workers who had coaxed it into being. Keller rode inside as the tank eased forward, a living proof of promise kept. What followed was theater with teeth. The 28-ton M3 lunged across the proving ground, slammed through obstacles, spat fire from its guns, and showed decisively that mass production had not neutered combat performance. A mock farmhouse fell like cardboard as the tank drove straight through it. Yet what the crowd didn't see was even more consequential. Behind that single machine stood a production system the military world had never witnessed. The line was alive. Component output was surging, supplier webs were being knotted together, and hundreds of workers were mastering specialized tasks, one operation at a time. In May 1941, the cadence quickened to 1 tank every other day. By June, a tank per day. Come July, 2 per day became routine. Meanwhile, Chrysler attacked the supply puzzle with the same relentlessness. 1 tank required roughly 8,000 individual parts. No company could make them all in-house. B.E. Hutchinson took the point, ranging across Michigan and adjoining states with a simple pitch. We need these parts to these specifications in these quantities on this schedule. Can you do it? Many balked at first, but Hutchinson put real weight on the table technical help, upfront funding for tooling, guaranteed contracts. The network spread through 1941 until it spanned more than 400 firms in 32 states. A Pennsylvania foundry poured final drive housings. Wisconsin shops turned out track pins. An Ohio forge delivered armor plates. Piece by piece, the pipeline thickened. The workforce transformed just as dramatically. In June 1940, Chrysler had exactly 0 employees with tank building experience. By August 1941, the Detroit arsenal employed 5 out of 800 people, most learning the craft from scratch. Chrysler set up training schools where each recruit rehearsed a single operation before touching production hardware. If your job was installing transmission mounts, you spent 2 days on dedicated fixtures first. Only then did you graduate to a real hull. The result: new hands ramped fast, with minimal drag on output. By September 1941, the arsenal was turning out 4 tanks a day. In North Africa, the M3 was already earning a reputation. British units receiving the type under Lend-Lease christened it the Grant, in honor of Ulysses S. Grant. They praised its reliability, even as they grumbled about its towering profile and that sponson-mounted main gun. Chrysler's engineers were already out ahead of those complaints. From the beginning, the Tank Committee had treated the M3 as a bridge. The sponson mount limited traverse and drove the height skyward. The real answer was obvious: a main gun in a fully rotating turret. Working with Army ordnance, Chrysler shaped what would become the M4 Sherman, the American icon of the war. The M4 inherited the M3's basic hull and suspension, but replaced compromise with a turreted 75mm gun. Watch how the changeover proved the power of mass production. The Detroit arsenal didn't slam the brakes to retool. It phased M4 components in while completing the remaining M3 orders. By February 1942, the line was building M4 Shermans exclusively. And the Sherman itself had been conceived with the line in mind. Chrysler engineers had pressed manufacturability into every contour and connection. So the system that birthed the first M3 could now deliver the tank America truly needed. The Sherman's very bones were drawn for the line. Hulls came as large castings or welded sections that needed almost no hand fitting. Turrets emerged from specialized foundries as single-piece castings, ready to accept their rings and guns. The drivetrain was a catalog of standardized interchangeable parts. Even the tracks were redesigned with one purpose in mind: to be made fast, in quantity, and without drama. Then came December 7, 1941, and everything shifted at once. The Japanese strike on Pearl Harbor pulled America fully into the war, and the measured climb in output turned into a sprint. Overnight, the Army's appetite for tanks exploded. The 1,000 that had looked audacious in 1940 became laughably insufficient by 1942. Chrysler's answer was acceleration, pure and simple. A plant that had managed 4 tanks a day in September 1941 was turning out 12 a day by March 1942. By July, 18 rolled off the line every 24 hours. Speed like that magnifies every flaw in the system. Bottlenecks flashed into view as soon as one station outpaced another. A shortage of qualified welders throttled hull production until Chrysler stood up welding schools that graduated 50 new operators a week. Machine tools were the next choke point, limiting precision parts, so Chrysler negotiated priority deliveries. Owen Skelton Now, general manufacturing manager, formalized the response with something he called production expediting. Picture teams of engineers circulating the floor like air traffic controllers, tracking each operation by the hour, isolating snags, and imposing fixes within days. Numbers became the arsenal's lingua franca. Daily output totals were posted high in public. Every worker knew the score for the day, the week, the month. Shifts developed a competitive edge, one crew trying to outbuild the next. And then came the month that made legend. December 1942, the Detroit Arsenal did what the skeptics had sworn could never happen. In 31 days, 896 Sherman tanks left the line and went to the Army 29 tanks a day on average. That single factory outproduced all other American tank plants combined. On its own, it outpaced the entire German tank industry. How? Through relentless, almost obsessive optimization. The line moved to a mechanical heartbeat. A tank advanced from station to station every 55 minutes. Workers, honed by repetition, turned complex operations into practiced gestures. Suppliers hit their mark so consistently that inventories could shrink. Quality control became a discipline unto itself. Gauges clicking, calipers reading, inspectors confirming dimensions and fit at every stage. That 896 tank month marked the pinnacle of wartime efficiency. Output stayed high afterward, but December 1942 remained the record of proof that tanks had crossed the boundary from craft to industry. Success bred imitation. The Army wanted capacity spread across the map, and new plants rose to meet it facilities run by General Motors, the Pressed Steel Car Company, and Pacific Car and Foundry among them. They adopted the moving line and precision methods, but none matched Detroit Arsenal's sheer volume and cadence. By the time the guns fell silent in August 1945, that single facility had produced 22,234 tanks across multiple models, about a quarter of all U.S. tanks built during the war. The machines themselves were never static. The Sherman evolved through a family of variants, each folding in improvements. The M4A1 bore a cast hull. The M4A2 ran twin diesel engines, a configuration favored for British and Soviet service thanks to fuel economy. The M4A3 mounted the Ford GAA V8. The M4A4 used Chrysler's own A57 multibank. Each change demanded adjustments on the line new fixtures, revised work instructions, but the underlying choreography held. That was the advantage. In the old Craftsman-bound system, a design change meant painstakingly rebuilding skills. On the line, it meant modifying jigs and updating the script. As for the Sherman's battlefield reputation, it has been argued, re-argued, and fought over ever since. In raw armor and gunpowder, it was inferior to Germany's Tiger and Panther. Sherman crews faced harrowing odds when confronting those heavyweights head-on. Yet the Sherman owned other strengths that mattered in the aggregate. It was reliable, staying in the fight while German machines fell out with mechanical woes. It was straightforward to repair, built around standardized parts and supported by crews who knew precisely how to swap and fix. And above all, it was present in overwhelming numbers. The arithmetic of production told the strategy. From 1939 to 1945, Germany built approximately 24,000 main battle tanks. Set the stage with a simple ledger of steel. Between 1939 and 1945, the Soviet Union turned out roughly 105,000 tanks. Britain managed about 28,000. The United States, late to true mass production until 1942, built on the order of 88,000 to 90,000 machines by war's end. And out of that American torrent, the Detroit Arsenal alone accounted for about a quarter. Numbers like these weigh heavily, but they are only the surface of the story. Beneath them lies the real revolution, not what was built, but how it was built. Before 1940, every great power treated tank construction as a cloistered, craft-specialized military work done in government arsenals by men whose skills took years to season. After the Detroit Arsenal, the world understood tanks as industrial products, creations of engineering discipline and production expertise. Ask yourself, what changes when you shift from a guild to a factory? Everything. Scale becomes possible because private industry can be mobilized. Training compresses from years to weeks. Supply chains spread across whole continents. And critically, capacity endures even as experienced hands leave for military service. When the guns finally fell silent, the arsenal did not fall idle for long. Chrysler continued to operate the site under government contract. Tank lines paused, then restarted with the Korean War. Between 1952 and 1954, the plant produced 3,143 M47 Patton tanks. In the 1960s, it built the M60. In 1979, the facility began turning out components for the M1 Abrams. Then came a corporate turning point. In 1982, under financial pressure, Chrysler sold its defense division to General Dynamics for $336.1 million. Production continued under the new banner until 1996, when consolidation shifted assembly to the Lima Army Tank Plant in Ohio. Walk the grounds today, and you won't find a silent relic. The Detroit Arsenal site now houses the United States Army TACOM Life Cycle Management Command and the Combat Capabilities Development Command Ground Vehicle System Center. A Michigan historical marker speaks plainly of what happened there. More than 22,000 tanks built, and a decisive proof that American industrial might could be shaped into a weapon. As for the principal actors in this drama, their paths diverged. Kaufman Thuma Keller steered Chrysler through the war years, rose to chairman in 1950, and retired in 1956. Albert Kahn died on December 8, 1942, just months after the arsenal reached its roaring peak. His ideas went on shaping factories for the rest of the century. William Knudsen, commissioned on January 28, 1942, served throughout the conflict as a lieutenant general, the highest rank ever granted to someone not already in uniform, and died in 1948. And the Shermans themselves, they fought everywhere the war went. They crawled ashore on D-Day's beaches in Normandy, pushed across France and into Germany, and island-hopped the Pacific alongside Marine Corps units. Through Lend-Lease, they served in British, Canadian, Free French, Soviet, and Chinese formations. Many survived to soldier on for decades. Israel fielded modified Shermans in the 1967 Six-Day War and again in the 1973 Yom Kippur War. Several South American armies ran Shermans into the 1980s. A handful still move under their own power, monuments not just to steel and oil, but to a moment when production capacity decided the shape of strategy. So we circle back to the essence. The metamorphosis from craft to industry happened because a small cadre of engineers and industrialists refused to bow to the old catechism. They looked at a tank and an automobile and saw no sacred divide, only mechanical assemblies made from thousands of parts. That change in eyesight, call it audacity, call it clarity, turned the factory into a forge of victory and the assembly line into a quiet, relentless instrument of war. Both, it turned out, could be born the same way, on moving assembly lines with specialized crews repeating precise operations in sequence. Obvious now, isn't it? In 1940, that was heresy. Seeing it required looking past the armor plates and the chrome, past the battlefield and the boulevard, to the shared skeleton of mechanisms underneath. It demanded engineering nerve to redraw military hardware against military resistance. And it took industrial self-belief to stake everything on production methods no one had ever attempted at such scale. In doing so, the Detroit Arsenal didn't just echo Henry Ford, it extended his idea into a harder world. Ford had proven that interchangeable parts in a moving line could deliver automobiles in unmatched volume and at low cost. Chrysler proved the same discipline could shape instruments of war with equal efficiency. Consider the strategic ripple. Without mass-produced tanks, American ground forces would have faced a crushing numerical deficit. Britain would have struggled to make good its losses. The Soviet Union, too, felt the surge thousands of American-built Shermans flowed east. The American capacity to turn out roughly 88,000 to 90,000 tanks between 1942 and 1945 was a feat no other nation could match. And about a quarter of that torrent rolled from a single site in Warren, Michigan. Yet the most important triumph may be the one you cannot see in a parade. The Detroit Arsenal didn't merely assemble tanks, it validated a principle. It showed that private industry could tackle government problems faster and more efficiently than government shops working alone. It demonstrated that engineering competence could outrank entrenched tradition. It confirmed that American industrial capacity properly mobilized was itself a war-winning asset. That realization shaped the peace that followed. During the Cold War, maintaining an industrial plant that could pivot swiftly to military output became doctrine. So too did the idea that American industry could simply outproduce any likely adversary. The partnership between private contractors and military procurement, born with the Detroit Arsenal contract, hardened into a permanent structure. Look closely, and you'll see another quiet revolution. Systems thinking before the term existed. These engineers didn't chase isolated fixes. They designed a complete organism components, suppliers, workers, assembly flow, and inspection, so each part supported the whole. They optimized not for heroic moments, but for throughput, stability, and change. The sunken trench along the assembly line, that wasn't a flourish. It erased a chronic undercarriage bottleneck by giving workers effortless access to the tank's underside. The supplier web, stretched across states and firms, introduced resilience, geographic diversification to keep parts flowing. The training pipeline supplied a steady stream of skilled hands, replacing losses and fueling expansion without stumbling. Scalability was the watchword. When command said double, the system could answer by layering shifts, enlarging supplier orders, and pushing more trainees through the schools. When new variants arrived, the organism adapted. Fixtures were modified, procedures updated, and the rhythm resumed. No need to relearn the craft from scratch. That is why the line could move from the M3 to the M4 without seizing up. Judge the achievement by the only measure that matters in war production: time per unit. The first M3, built in April 1941, consumed about 500 man-hours. By December 1942, M4 Shermans were rolling out at roughly 150 man-hours. More than a 300% productivity gain wrung not from luck, but from relentless iterative improvement. Every month, engineers read the numbers like scripture. Which operations overran? Where did defects cluster? Why did a particular station slow? Fixtures were redesigned, methods rewritten, tasks rebalanced. Nothing was sacred but the schedule. This culture of continuous improvement, common in civilian auto plants, alien in military arsenals, used to fixed procedures, was the indispensable catalyst for the volumes the war demanded. And what did it cost to build the engine that built the tanks? The bill was substantial, but modest beside the output. About $20 million for the facility itself, and another $30 million for equipment and tooling. Think about that the next time you see a Sherman on a plinth. Not just a machine of steel and oil, but a proof of concept cast in concrete and numbers and argument made once and for all that the assembly line could be turned into a weapon. By the war's end, the Detroit arsenal had become a financial and strategic triumph on a scale few could have foreseen. The total investment, factory, tooling, machinery surpassed $100 million. Yet from that investment came 22,000 to 134 tanks, with a combined value exceeding $2 billion. The return on investment was staggering by any metric, but money only hints at the real dividend: strategic advantage. The arsenal's production might give American ground forces something no strategy alone could guarantee: numerical dominance in armored vehicles. From the deserts of North Africa to the forests of Germany, that superiority changed the rhythm of battle itself. Without the output from Warren, Michigan, and from the sister plants it inspired, the war's final balance might have tilted very differently. At its heart, the story of the Detroit Arsenal is about imagination, the courage to see possibility where others saw impossibility. When Kaufman Tuma Keller told William Knudsen, "I've never seen one of these things," he was confessing ignorance, not incapacity. Chrysler's engineers didn't yet know how to build tanks, but they knew how to orchestrate complexity, how to assemble thousands of components into a working machine. That confidence, that conviction that any problem could yield to engineering discipline was distinctly American. Across the Atlantic, manufacturers clung to the belief that tanks were exotic creations, forever separate from civilian industry. In Detroit, they were simply machines' problems to be solved, processes to be optimized, parts to be made to fit. The Arsenal vindicated that philosophy utterly. In 9 months, Chrysler went from zero experience to delivering finished tanks. In 18 months, it was exceeding the Army's targets. In 3 years, it had outbuilt entire nations. The people who accomplished it were ordinary men and women performing extraordinary work. They didn't storm beaches or liberate cities. They built the machines that made those feats possible. This was industrial democratization on a scale the world had never seen. In earlier wars, weapons were the province of master artisans working in guarded arsenals. Now they poured from the hands of housewives, farmers, recent graduates, shop clerks, people who learned a single operation and perfected it through repetition. The Detroit Arsenal became both the symbol and the proof of that transformation. It showed irrefutably that private enterprise could outbuild government arsenals. It demonstrated that methods born in peacetime industry could forge the weapons of war. It gave substance to Roosevelt's arsenal of democracy, and it confirmed that in modern conflict, industrial power was as decisive as battlefield tactics. Drive past the site today and you might not guess its history. Yet the legacy hums beneath the surface. The M1 Abrams, the backbone of today's U.S. Armored Force, is still shaped by the same principles: modular design, supplier integration, precision tooling, and flow line assembly. Modern defense manufacturing, private contractors, distributed supply chains, industrial production techniques all trace their lineage back to that factory on 113 acres of Michigan soil. The transformation that began their craft to industry, tradition, to system reshaped how nations equip themselves. It proved that engineering ingenuity could smash through convention, that no problem was too intricate for disciplined design, and that the same logic that put America on wheels could also put armor on the battlefield. The Detroit Arsenal did more than build tanks. It built the blueprint for how modern wars would be fought and how industrial power could decide their outcome. And in the end, it proved something greater than steel or strategy could ever convey, that American industrial capacity, when truly mobilized, could forge the tools of victory in volumes that no enemy could hope to match. This was the invisible weapon that helped win the Second World War. Not superior technology, though American machines were good. Not better tactics, though many were ingenious. Not sheer abundance of resources, though those mattered too. The real edge lay elsewhere, in the audacious decision to treat war as an engineering problem and to solve it with industrial logics. When Kaufman Thuma Keller picked up that telephone on June 7, 1940, he couldn't have foreseen where his plain-spoken reply would lead. "I don't know," he had said, "but we'll find out." In that moment, he gave voice to the defining American instinct that ignorance is only temporary, and every problem yields to method and persistence. From that mindset grew a system that changed the nature of warfare itself. The engineers who mapped it, the workers who manned the lines, the suppliers who fed the flow, all of them became parts of a single, sweeping achievement. They proved that tanks could, indeed, roll off assembly lines like automobiles, that complexity was not an obstacle, but a challenge, and that American ingenuity, when tested, could make the impossible practical. The Detroit Arsenal deserves remembrance not only for what it produced, but for what it revealed. It wasn't merely a factory, it was a laboratory of thought. It showed that the hardest problems often crumble when someone asks the right question and refuses to accept impossible as anything more than untried. The tanks themselves are mostly gone now, melted down or standing mute in museums. The great building has been largely demolished. The men and women who filled it have passed on. But the method endures. The insight that even the most intricate machines can be mass-produced lives on in every modern factory. And the conviction that engineering can solve production puzzles survives in every designer who stares at a complex product and asks, not can we build it, but how do we build it efficiently, reliably, and at scale? That question, first asked and answered in Warren, Michigan, between 1940 and 1945, reshaped the modern world. It made mass-produced warfare possible. It confirmed that America's industrial methods could outperform the old European craftsman traditions. It proved that private industry, given a clear goal and freedom to innovate, could outproduce government arsenals bound by habit. And it demonstrated something deeper still, that when engineers are handed an impossible problem, they sometimes solve it by refusing to recognize impossibility. This is why the Detroit Arsenal story still matters. Not just because the tanks are fascinating, though they are, not simply because World War II was history's hinge, though it was. It matters because the Arsenal represents a philosophy of problem-solving that remains vital today. See the underlying pattern, not the surface difference. Apply proven systems to unfamiliar challenges. Design wholes, not fragments. And never ever assume that it can't be done means anything final. In 9 months, Chrysler went from never having seen a tank to building them in quantity. In 18 months, they were surpassing every projection. In 4 years, they had produced more armored vehicles than most nations managed in the entire war. All this because a group of engineers looked at a military crisis and saw an industrial puzzle. They ignored convention. They defied pessimism. They solved it. That, more than any tank or tally, is the enduring legacy. Proof that when confidence, engineering discipline, and systemic thinking combine, impossibility is merely an invitation. When someone says, "It can't be done," the right response remains, "Show me why not, and let's find out." That answer, spoken with conviction, once built an arsenal that helped save democracy, and it remains to this day the blueprint for doing the impossible.